Let P1 be the set of all primes, 2, 3, 5, 7, so on. And for each integer n, let Pn be the set of all prime multiples of n, 2n, 3n, 5n, 7n, and so on. Which of the following intersections is non-empty? Okay, so I think we're looking for something about numbers being relatively prime, maybe? Or something like that. I mean, maybe there's some kind of theorem that you can quote here. But there's probably some theorem, that number theory thing, that just kind of gives you the answer right away. But I think I'm just going to kind of brute force it, more or less, and go through each example. So A, it will not be the case, right? P sub 1 intersect P23. So these are all primes. These are all multiples of the number 23, and therefore not prime. So these can't possibly intersect. B, we have P7 intersect P21. Okay, this might work, right? P7. Wait, hold on. P7, well, P21 is equal to P 3 times 7. So can I find a prime times 7, which is equal to another prime times 21? I'm seeing now that this is probably the way that I should be solving this question. So I have 7p is equal to 7 times 3q. So p is equal to 3q, which is a contradiction because we need p to be prime, and it clearly isn't. Yeah, so let's just work through each example like this. P12 intersect P20. So I need 12p to equal 20q. This is 3 times 4p is equal to 4 times 5q. 4 cancels, and I have 3p is equal to 5q, which, and I can solve this, right? P equals 5, Q equals 3. So that'll work. So we can in fact find the numbers in here that in fact give, that exist in both sets. I guess it's 60, right? 60 will be an element of P12, and 60 will be an element of P20. So this is the answer, C. Just for fun, I'm going to go through some of the other sets here. P20 intersect P24. This implies we need 20p to be equal to 24q. So we have 10p is equal to 12q. 5p is equal to 6q. And this is clearly not possible for two primes, p and q, right? P will have to be even and greater than 2. So not possible. And I'm sure we can just continue the same type of argument. P5 intersect P25. So we need 5p is equal to 25q. So p is equal to 5q. Again, a contradiction. P has to be prime, and that contradicts it. Yeah, so the answer is C. I wasn't really sure how I was going to approach this originally. Like I said, I was just going to kind of, my first instinct was to, when no simple method appeared, was to more or less just brute force and look for intersections in these sets. But when you write out what it means for these sets to have non-zero intersection, it means you can find a prime P and a prime Q where these numbers are equal. And then just argue through factors and primality of things and so on. Yeah, so nice little problem. Thanks for watching.